Hello students, today we will be dealing with topics that are actually associated with non-ideal fluids. Now within this we will be dealing with topics like viscosity and surface tension, and we will be seeing how these properties manifest itself in the real physical situation. So let's start the topic. Let's start the new topic, viscosity. What is viscosity? The viscosity of a fluid can be defined as the measure of how resistive the fluid is to the flow. Now it is analogous to the friction of the solid bodies. Now a friction that occurs in solid bodies, when the two solid bodies have their contacts, their surfaces in contact, it generates friction. What happens when the solid surface is in contact with the liquid, or it's like liquid surface is in contact with the liquid? Again, there is a similar analogous frictional kind of character that is called the viscosity of the fluid. Now it is the measure of how resistive the fluid is to flow. How resistive it is to flow means how easily it can flow will mean it has a low viscosity. How difficult it is to flow will have a high viscosity. Like the flow of the oil, it is more viscous than the flow of water because the flow of oil is more resistive. It tends to resist the free flow. Now it is because of this frictional nature, it serves as a mechanics for transforming the kinetic energy into thermal energy. Now this viscosity, similar to the friction force that happens in the solids, this tends to convert the kinetic energy into thermal energy. Now if you see here, this is a moving plate, this is a stationary plate. Now this is a fluid that is flowing. Now the moving plate, whatever is moving, suppose this is moving with a velocity v, liquid that is in contact with it also moves with a velocity v. And the liquid that is in contact with the stationary plate is at rest. The liquid surface, exactly if you consider this surface is at rest, it's not moving, and this liquid surface is actually moving with a velocity v. Now if you consider the intermediate layers between here to here, now the velocity of these liquid fluid layers is decreasing. The liquid layers, they are decreasing. It's coming from v to 0. So there is a resistance that is transferred from this layer to this layer. This is the lamina, this has been shown here. This is the flow with successively higher velocity. Means here the velocity is 0, velocity is increasing and it reaches to v, which is the velocity of the moving plate. Now, we will see quantitatively like what is the expression that we get for this viscous forces. Now the force of viscosity in a fluid, it is found to be proportional to the surface area of the contact. Now if you see here, this is a moving plate moving with a velocity vector v. This is a fluid that is moving. This is a stationary plate. Now, the fluid that is in contact with this is moving with a velocity v, and the fluid that is in contact with this has a velocity 0. So, now this force, viscous force, that will be applied by the liquid. How do we measure it? What is the force that we should apply so that it moves with a constant velocity v? Because if you don't apply this force, it will be stopped because it is being resisted by the viscosity. Now, so to keep it moving with a velocity vector v, we drag it with a force F. And this force, now it is moving with a constant velocity. Now this force of viscosity, it is proportional to the surface area A of the contact. Means whatever is the surface area in contact, it is proportional to that. Very dissimilar with the friction force that we have in the solids, where it is independent of the area of contact, and the velocity gradient, and it is also proportional to the velocity gradient. So the viscous force is actually eta A dV by dx. So this is actually eta times area v by L, where v by L, or if you write in terms of dv by dx, means what is the change in v with respect to the change in distance. So if you have taken L, we may write it as dv by dl. So if you move a distance dl, suppose like this, what is the change in velocity? It was v here. What is the velocity? Suppose it is v minus dv. Velocity is decreasing in this direction. So the velocity gradient will be dv by dl. Now this force is proportional to the area in contact and proportional to dV by dl. Now this eta that you see, this is the constant of proportionality. This eta is called coefficient of viscosity. This is a proportionality constant. It is a property of the fluid. A surface which has a higher eta means it's more viscous, lower eta means lower viscosity. The formula for this, now if it's varying very uniformly, we can also write it as V by L, the velocity gradient. If it's uniformly decreasing, changing, we can write it as V by L. Otherwise, this is the force and this is the viscous force. It is proportional to the area and the velocity gradient. Let's move to another topic, surface tension and capillarity. Now, what exactly is surface tension? You may have seen these types of things in your surroundings. After rain or in the morning, you may find out water droplets hanging like this from the trees, branches. Now, why this happens? Now, the surface of the liquid, any liquid that you see at rest, it's not perfectly flat. Although at many of the times it may appear to you that it's generally flat, but it's actually not in most of the cases. Obviously, it can be flat in very few cases that we'll discuss later. It curves either up or down at the walls of the container. At the walls of the container, it either curves up or curves down. It's like this. Suppose we have the liquid kept like this. Liquid could be either like this, it's curved down, or the liquid could be filled, means this is filled like this, it could be like this. This is the liquid that is filled up. So it could be either this, it could be either this, and a very special cases it could be this. Obviously this can also be possible, but this is a very special case that we'll discuss later on. Now this is the result of surface tension. Now why this happens? This curve that you see, the curved surface, why does this happen? This happens because of surface tension. This is happening because of the surface tension of the liquid that is filled up in any container. Let's see what exactly is this surface tension. Now you may have seen these kinds of situations, like if you put a pen like this in a liquid that is sufficiently viscous, you may observe this, that it's still there, it's hanging, it's not getting sink within this container. Or you may have seen some insects floating over the surface of the water, it's not going inside. How is it that these two are able to resist their sinking down within the container or within the liquid in which it is kept? You see these surfaces here, here. Now the surfaces are curved up. Now here also the surrounding surfaces, they are a bit curved up. Now the reason for this is surface tension, and that way we are going to discuss now. Soaps and detergents. The soap and detergents that you see in your home, it lowers the surface tension of water. It lowers the surface tension of the waters, means the property of the liquid by which it resists the sinking of, like we have seen a pin or linchpin or an insect. It is lowered by soaps and detergents. This allows the water to penetrate the materials more easily, and then it's becoming it's more easier to penetrate. Now water molecules, they are more strongly attracted to the glass than they are to each other. You see the water molecules here. Consider this molecule. Now this water molecule, this is attracted more strongly by a nearby or the other water molecule. These water molecules are attracting with a higher force than it is attracted by the molecule of this. If you consider this molecule, which is of the glass, this force is smaller. This force F dash, and suppose this is F, then this F dash force is actually less than F. The molecules, each molecule is being attracted by the molecules that are present within the surroundings. Now within the surroundings, there are two kinds of materials. One is of its same nature, means material of same medium, and another is the material of the surrounding medium. Surrounding medium means in which it has been contained here, the different medium. Now the force with which it attracts, it depends on the materials and the water. Now when you put water, they are attracted more strongly to glass than they are to each other. So the force that is present here, F dash, is actually it's greater than capital F. So the force with which it is attracted by this is greater than this force. What happens due to this? Because of this greater attraction, it tends to pull up, tends to get pulled up. So what happens in mercury? In mercury, as you can see, the force with which this water molecule, if we consider, with which it is pulled in this direction by the water molecules is greater. Now this force F, and suppose the force attracted by this is F dash, here F is greater than F dash. So what happens? It tends to pull it down. So you can see the surface tends to come down. It tends to curve like this because this force is greater than this F dash force. Now you can see what happens to a glass tube in water. If you put a glass tube in water, the water rises like this and the surface tends to become like this. Again, this is because the force with which this attracts, this F dash, this is greater than this force. F dash is greater than F, surface becomes like this. It is dragged in this direction because of the greater force. Now this force that you see, that is acting between different mediums, this is called adhesive forces. Between different mediums it is called adhesive force. Between the same medium it is called cohesive forces. This force is called the cohesive force and this force is the adhesive forces. So when the adhesive force is greater than cohesive force, the surface tends to become like this. Here you can see that the cohesive forces are greater. Here the cohesive force is greater than adhesive force. And the surface tends to become like this. And this normally happens in the case of mercury. When you put mercury within and then a glass tube, within that surface tends to become like this. Now this action that you see means when you put a capillary, this is container containing the liquid. A capillary is any narrow glass tube with a very small diameter. If you put it within this, either this will happen or this will happen. Now this property of the liquid, so by virtue of which it rises within a narrow capillary tube or it gets suppressed like this, is called capillarity. Now if you see at the microscopic view of the surface tension, the cohesive forces among the liquid molecules are responsible for the phenomena of surface tension. Now the surface tension, it is arising due to the cohesive forces. Because if you consider this molecule at the surface, there are no other water molecules above it. So it is being pulled in this directions, in all the directions below, like this. So there is a net force in the downward direction. If you see, the resultant of this is a net force in the downward direction. Now consider any water molecule in the bulk of it. What is happening? It is being attracted in all the directions by the forces. So the net force on this is 0. But here there is a net force and it is in the downward direction. Now what this does? This makes the surface stretched. It's like this surface is in a state of tension. It's like a balloon that has been stretched. All the molecules are in the state of tension, and so that is the reason it has been given the name surface tension. The surface of the liquid is actually in a state of tension. It is because the molecules on the surface, they are being attracted in all the direction, from all the directions in the downward manner. But all of the molecules that are in the bulk, they have a net force of 0. Molecules on the surface, they have a net non-zero force that is generating this surface tension. Now in the bulk of the liquid, each molecule is pulled equally in every direction by neighboring liquid molecules, resulting in a net force of 0. Now the molecules at the surfaces, they do not have other molecules on all sides of them and therefore are pulled inwards. Therefore they are pulled inwards. This creates some internal pressure and forces the liquid surfaces to contract to the minimal area. Now since there is a force that is acting from in the surface from all of the directions, right? Now this force, this you see, whatever is acting on the surface, it tends to contract it to a very minimal area. It tends to make the surface with minimum surface area. Surface tension, this is the property of the surface of a liquid that allows it to resist an external force. Now since the surface is in a state of tension, the whole surface, the surface of the liquid, it is in a state of tension and it tends to resist an external force that is being applied on it. Now if you see here, this is the liquid. Now this whole surface is in a state of tension. This whole of the spherical, now if you see, this is like a spherical drop. This is in a state of tension. Now what it does, this resists any force from outside. This tends to resist any force from outside and so it remains like a drop. So it remains, it's not like it's flowing down. It's because of this whole drop being in a state of tension. But as its mass increases, what will happen? Under the weight of its mass, it tends to break down. This force becomes, the force that is being exerted from the bottom becomes higher. Because of heavy weight, it becomes higher, and then it overcomes the surface tension and it flows down. Then it no longer remains like this. So you will only find small drops acting like this in a manner where surface tension property is more visible. It is revealed in floating of some objects on the surface of water, even though they are denser than water, in the ability of some insects, the water sliders, to run on the water surface. We have seen how this shows the property of the surface tension, like the insect. Because the whole surface is in a state of tension, so an insect, it can rest on it by under the influence of that. Now, we'll try to define it quantitatively, surface tension. Now, there is a flat soap film bounded on one side by a taut thread of length L. Now, if you see this is a soap film. Now, this is a film. This is a film. This is a thread of length L. This, see from here to here. This is a thread. Now, it has been dropped in a soap film. So, what happens that this soap takes the shape. Now, if you try to pull it, this thread, if you try to pull it by a force F, the surface tension, which is denoted by the symbol sigma, small sigma, it is defined as the force along a line of unit length, where the force is tangent to the surface but perpendicular to the line. Now, if you see here, now in this case, surface tension, which has been defined for a liquid in contact with a surface, it is defined as, sigma is defined as the force acting per unit length. This is how it has been defined. Means if I have to apply a force F to keep it in a state of rest, because what's happening is, because the liquids here they are trying to pull it in this direction because of surface tension forces. So in order to keep it in shape, in order to keep it like this, you need to apply a force. Now this force per unit length of this surface, you can see this is a surface, the length of this is defined as surface tension. Now if you see here, the thread, it will be pulled towards the interior of the film, this thread. This is being pulled towards this. This will give you forces sigma into L. Now it is being pulled in this direction with sigma L. But this in this case, it is actually this 2 sigma L. Why this 2 sigma? It's because the soap surface that you have here. Now this surface has actually, the soap film, it has actually 2 surfaces. One from the, whatever you see from the top, and another one is coming from the flip side. Means if you see from this side of the plane, inside the monitor, and then whatever is observed from the side behind the monitor, from the both sides there is a surface. Obviously there is a very microscopic difference between the 2 surfaces. Means the surface, it has a finite thickness. So there are molecules on the upper surface and then there are molecules on the lower surfaces. Definitely they are very, the thickness is very minuscule, but it is significant on the microscopic level. So all the molecules on the first surface, they are also pulling it back, and the molecules on the lower surface, they also pull it back. So it's like 2 sigma L forces that are acting in the backward direction, like this. So it is being pulled not only due to this upper surface but also due to lower surface, because this soap film, it actually has a finite thickness. So the actual force that will act is 2 sigma into L. The sigma is the surface tension, L is the length of this. Surface tension is therefore measured in forces per unit length. So this is force per unit length. Having gone through our video lectures and video solutions may have cleared most of your doubts. For any further doubts, you may visit our site www.askIITians.com. On the site, you will find a tab called Ask a Question. Click on that tab. Clicking on the tab will take you to the next page where you will find an icon Ask Experts. If you want to ask any questions, you can select the category of the questions. Like if you want to ask question from suppose wave motion, click on that option wave motion, paste your doubts here. If you want to attach some image of the question, you can attach the image also. Your question will be answered within 24 hours to 48 hours. So students, we have seen viscosity and surface tension. Now in the next topic, we are going to discuss some other aspects of the surface tension and surface energy. So stay tuned with Ask IITians for the next topic.